This program, ADCCOS, demonstrates analog sampling and reconstruction of a cosine and allows one to demonstrate the effects of aliasing. The input signal is a cosine of frequency f, which can range from 0 to 4 Hz. The top and middle left panels show the magnitude and phase of the cosine. The bottom left panel shows the time function. When the program starts, f is set to 0, so the magnitude only consists of one impulse at 0 frequency, and the phase is 0, which corresponds to a constant x of t. To change the frequency of the cosine, either drag it out on the magnitude plot, or use the slider, or enter a value in the edit box. The phase of the cosine can be adjusted by dragging on the phase dots, the slider, or entering a value here. The corresponding time function, x of t, appears in the lower left panel in blue. The thin gray line is the cosine with a phase of 0, just for reference. Select a sampling frequency, f sub s, either by dragging in the top middle panel here, or by using the slider, or by entering a value in the edit box. The transform of the sampled signal, x sub s of f, comprises replicas of x of f, that is, a pair of impulses, at multiples of the sampling frequency, which are indicated by these little green triangles. In order to keep straight which impulses in this display are associated with each sampling frequency, check this box. Now each pair of impulses of a replica is given a color and a number that indicates the multiple of the associated sampling frequency. So the baseband is 0, the first image to the right is 1, the first image to the left is -1, and so on. For clarity of display, the amplitude scale of the transform of the sampled signal is normalized to the sample frequency, so the height of the impulses will not change as the sample frequency changes. The shaded cyan region in the upper and middle panels here shows the frequency range of the ideal low-pass reconstruction filter, which is always set to 1/2 of the sampling frequency by default. The output of this reconstruction filter is shown in these right panels, the magnitude y of f on the top and the phase in the middle. The bottom panel shows the output time waveform y of t. In this case, we are sampling well above the Nyquist rate, so the output is equal to the input. The lower panel here is a display of the sample time signal xs of t that corresponds to the transform xs of f above. Initially, the display is blank. However, as the lower slider is moved, a series of small red squares appear that mark the locations of the impulses in xs of t. In this case, since the sampling rate is 4 Hz, there are 4 samples per second. 1, 2, 3, 4. Associated with each sample is a thin gray trace that corresponds to the impulse response of the ideal low-pass reconstruction filter to the corresponding impulse of x of t. Setting this control to partial sum reveals a blue trace that corresponds to the partial sum of the output of the reconstruction filter to all the impulses currently visualized in the plot. As you move the time slider to the right, more impulses appear. Setting this control to sum shows the complete output of all the scaled and shifted sinc functions y of t. Unchecking this link filter control allows you to set the bandwidth of the reconstruction filter separately from the sample rate, either by moving the slower slider or by entering a value in the edit box. As you change the value of the bandwidth of the reconstruction filter, notice that the sinc functions change, but that as long as the bandwidth of the reconstruction filter is greater than the bandwidth of the cosine, the output is the same as the input. As soon as you lower the bandwidth of the reconstruction below that of the cosine, goodbye cosine. Now, as long as the sampling frequency is above the Nyquist rate, there will be no aliasing. However, lowering the sample frequency will cause aliasing. To see this effect clearly, it's first useful to expand the frequency scale with this control here. And let's also turn on some sound that corresponds to the output y of t. Let's now decrease the sample frequency, keeping the reconstruction filter's bandwidth at 1/2 the Nyquist rate. Here we are still above the Nyquist rate, so the image replicas do not overlap with the baseband. However, when we lower the sample frequency below the Nyquist rate, we will get aliasing. Now, the baseband replica, denoted with the zeros, falls completely outside the bandwidth of the reconstruction filter, but impulses from the two adjacent image replicas, denoted 1 and -1, fall inside the filter, and the frequency of the output cosine has gone down to 0.2, as you can see in the frequency and time panels. Finally, by turning off the color, you can see that this aliased waveform is indistinguishable from a 0.2 Hz cosine that has been properly sampled above the Nyquist rate at 1.2 Hz. This program is one of a suite of programs that I have developed to explain DSP concepts to my students during lectures. There are now well over 24 programs covering many aspects of the material in the book, including complex exponentials and sinusoids, convolution, the DTFT, pole zero plots and their relation to frequency and impulse response, A to D and D to A conversion, including upsampling, downsampling, resampling, and aliasing, the design of many types of FIR filters and their application to the filtering of speech and other signals, the design of IIR filters, circular shift and convolution using the DFT, the discrete cosine transform, and the short-time Fourier transform. A selection of these programs is being made available to instructors who are currently adopting the book in their classrooms. For further information, please visit cambridge.org/Holton.